Okay, let's get started. So I'm going to forego the announcement slide since we're pre-recording this lecture, and I'm just going to jump right into it. So I'm recording this lecture a little bit in advance, so hopefully we will get to the point where we're at by the time this lecture goes live. But what we're going to do is basically discuss an additional aspect of designing discretely braced beams. And the way that I break this down in the class is I first show you how to design for what I call low CB values, and then for what I call high CB values. And I think today's lecture will definitely help you discern what I mean by low versus high CB values. So with that, let's go ahead and jump right in. Let me see. I'm running with a few different monitors here. Okay. So let's recall the process and make sure that we're all comfortable with how we design discretely braced beams in general. So the first thing that we do is we compute our demand, our moment and shear demand. Since we're in design, we're using an assumed self-weight of the beam in question. Then we compute a moment of inertia requirement based on our deflection limits, typically a live load deflection limit. And then we determine our CB and our LB for design. If possible, we'd like to be able to look up CB. Otherwise, we'll have to compute it if the structural analysis case is too complex. The LB value for design, we can get that from the just from the beam itself. And then what we do is we go to table 310. We go in on the x-axis with our unbraced length, and on the y-axis with our MU max divided by CB. So we divide out the effective CB for our problem so that we can go into table 310, because as you'll recall, table 310 just charts out the capacity assuming CB is 1. And then that will give us a trial section. And make sure that for that section that the moment of inertia is big enough. If the moment of inertia isn't big enough, ignore all this and just select a section based off table 3.3. But if the moment of inertia is big enough, analyze the section and verify that it has adequate shear and moment capacity and that it meets deflection requirements. One other thing I will mention, and let me move my camera a little bit out of the way so that you all can kind of see what I'm talking about here. I'll just move it up here. So if you have a beam like this one here on the slide, and so this one is one that's a little bit more complicated, a little bit more involved. We have 3 different unbraced lengths. So each segment's going to have a unique LB. Each segment's going to have a unique maximum moment, and each segment is going to have a unique CB. So in design land, that might be a little bit hard to select, might be a little bit hard to figure out where you're going to start. So what I would do is pick the segment that has the largest MU divided by CB or the largest LB. There's a good chance that's the same segment, but if not, I would go with the one that has the largest moment, just for the purposes of picking a trial selection. Or a trial shape, because once you get that trial shape, you can analyze it. If it doesn't work, you can iterate. When you're in analysis land, you do need to analyze all of the segments to verify the capacity. So you're going to have 3 different unbraced segments. For each of those segments, you're going to have a phi-mn, and you need to compute the phi-mn for all of them. Some of them could be neglected by observation. So for example, if you look at these segments, let's say on this problem here, and you draw the moment diagram, and you find that the middle segment has the highest CB and the lowest moment, you could ignore that segment just based on common sense. But when in doubt, just analyze all of them. And for moments, the section that governs is the one that has the largest performance ratio or efficiency, just the MU divided by phi-mn. This note isn't really going to affect the example that we're going to do here in a bit, but I thought it prudent just to mention that as we get into the design we are going to look at today. Now, I've mentioned at the beginning of the lecture that there's a problem, or today's focus is what I'm going to call high CB values. And the reason why is because there is a problem with high CB values, and the problem is that they can lead to a false positive associated with design. So for this quick exercise, I would recommend that you get your manual out if you haven't already done so and follow along just to kind of show you what I'm talking about here. Okay, so I want to go through the design process with you real quick, and I want to pick a section for the following data. So let's say I've analyzed a given beam, and I've found that the maximum moment is, let's say, 10,020 foot kips. I know that I need a moment of inertia of 2,800 inches to the fourth. I know that my CB value is 2, which is a pretty high value. And our unbraced length is 20 feet. And there's nothing really magic about these values. They just help us, they will help illustrate the issue with high CB values. So how do we go about design, and how do we go about selecting using table 310? Okay, well, what we do is we go into table 310. On the x-axis, we're going to go find 20 feet. And on the y-axis, what we're going to do is we're going to take mu divided by CB. So we're going to divide that out, and we find a moment of 510 foot kips. So that's just 1020 divided by 2. So what I want you to do is, and while I'm yakking on, you can probably get your manual and open up table 310. But I want you to go to table 310, and I want you to go on the x-axis with an LB of 20 feet and the y-axis with 510. And remember, what you're doing is going to that point and looking up and to the right and finding the first solid line segment that you can find. Find a trial section that works. And I'll give you a second in case you want to pause it. Okay. After that, if you do this correctly, you should find a W24 by 84. That's the section that you should find. And I'll actually have that animated here in a few later slides, but in case you wanted to do that. Now, what I want you to do is go to the 24 by 84. I want you to go to table 3.2 to the ZX tables, and I want you to look up the sections Phi and P. It's plastic moment capacity. And I'll give you a second on that in case you want to pause. And when you look that up, you should find a capacity, a Phi MP of, that's the plastic moment capacity, of 840 foot kips. Now, I guess a final prompt for pausing is maybe you ought to pause the video right now and look at this slide and see, does anybody see a problem with what's going on this slide? And it is much more apparent if you look at all the data here on the slide. But in case it's not apparent, let me kind of show you what's going on. So here's the problem with what we just did. Okay, the maximum moment on that beam was 1020 foot kips. So we can see that from the previous slide. The maximum moment is 1020 foot kips. Now what we would do is we would take that trial section and typically we would analyze it in order to validate its capacity. But we don't need to do any analysis to see that its maximum possible capacity is Phi and P, and Phi and P is only 840. So without doing any math, I can tell you that that trial section I picked, it's no good, okay? The problem is that this process led to a false positive, okay? And here's really what happened. Whenever you have a CB value, CB serves to increase Phi-Mn. So because it increases Phi-Mn, when we go into table 310, we divide the applied moment by CB so that we're able to use that chart with a CB value of 1. But the problem is you can't increase the moment capacity past the plastic moment. The plastic moment is the cap, okay? And because of that, and because of the way we divide that, you can't really count for that cutoff where the CB cuts off the capacity at MP. You can't really account for that in the design phase. So what's happening is that you're looking up a trial section that looks good according to table 310, but it's not, okay? So this is one of those reasons why you definitely need to analyze the trial section once you have one, just to verify that it works. This is really why that's very important. Okay, so if we go to that example, so if you followed along with the manual, you should have been on this chart. I don't know what page that's on because I have my manual open digitally here. But it should be, you should have found this, and so you go to 20 feet and 510, and so you're hugging that left end of the table, look up and to the right, and that's the section that you look. So what happens when you get a false positive? So that's the section that you looked up. If you get a false positive, just go to the next one. And then if that doesn't work, go to the next one. And you keep going to the next one until you find one that works. And just so you're aware, this is a point I would mention. As you can see, sometimes these lines get a little bunched up, and it might be a little easier if the labels are a little tough to maybe trace upwards. Usually you can trace up and to the right, but if it's easier, you might want to trace upwards. All right. So how do you handle a high CB value from an efficiency standpoint in your calculations? I think it's a good idea to set up a table. I'm an engineer. I like setting up tables. So let's take this problem and let me kind of show you how it would work out. Okay, so the first section that we looked up in this example was a W24 by 84. We're looking that up, or we're looking a section up to have a flexural capacity, or we need a flexural capacity of 1020 foot kips, but the plastic moment is no good because, well, the plastic moment is lower than that, and since the plastic moment is the largest capacity that the section can withstand, this section isn't going to work. Now, we do need a 2,800 inches to the fourth moment of inertia, but what's the actual moment of inertia for a 24 by 84? Who cares? Because the section doesn't work, okay? So you'll see that how that evolves here in a second. So the next thing we would do is we would go to table 310 and we would say, okay, let's trace up to the next section that we find, and the next section is a W27 by 84. Again, we're designing for a 1020 foot kip applied moment. Its plastic moment is 915 foot kips, so it's no good. And again, who cares about the moment of inertia if the section's no good? So the next section that you go up and you find is a W30 by 90. It has it needs to withstand an applied moment of 1020 foot kips. Now, the W30 by 90 has a plastic moment of 1060 foot kips. So does it work? I'm not going to say it's good because I don't know. I have to go through and analyze the section, but it's probably a valid section to start my analysis. So at a minimum, this is starting to look like a better choice. Okay. Again, we don't know if it's going to work, but it's at least a worthy section to analyze. As for the 2,800 inches to the fourth, now it's probably a good time to actually report what is the moment of inertia of a W30 by 90, and it's 3610. So this is going to work. So now we've got something that's worth analyzing. And I would say at this point that if your moment of inertia is still no good, abandon this table 310 iteration altogether and just pick a section based on table 3.3, because serviceability is most likely going to govern your design. And I think the easiest way to wrap your head around everything that we're talking about here is to go through and do an example. So what we're going to do is we're going to design this discretely braced beam, and let's sort of digest this problem a little bit. So I've got a problem that I'm going to design. I've got to design this beam. It's a simply supported beam that's 20 foot long. It's braced at the ends and at midspan. So the beam is 20 foot long. The unbraced length is 10 feet. Okay. And so again, this is one of those areas where I definitely want to make sure, I'm already making errors here. So this is 20 feet. LB is 10 feet. I want to make sure that that's clear. We've got a simply supported beam with a distributed load of 100 pounds per foot across the span. That comes from the self-weight, and we're assuming that the beam the beam weighs 100 pounds per foot, and that's the only dead load that we're seeing. I see here that the dead load shown does not include the beam self-weight, but that's actually what we're applying. So that note is probably worded kind of poorly on my part. Apologies for that. But we do have a live load at midspan of 65 kips. So I have gone ahead and already told you what the CB values are for each of these segments. This is one of those problems where you can probably look up from table 3.1 or compute it, but we're going to go with a CB of 1.67. We are going to design the beam to meet an L over 360 live load deflection limit. And so with that, let's go ahead and just jump right in. As I say here in this gray note, just be prepared because there is going to be a lot of flipping back and forth on this problem from two different design tables in the manual. I made it a little easier in the recording, but as you're following along, just be prepared for that. Okay. So what I'm going to do is I'm going to start. I'm going to go through this process the same way that we would normally go through a design problem, and that's compute MU and VU. Okay, I think at this point, I think we're all in agreement that those are pretty easy assumptions at this point. So we've got a self-weight of 100 pounds per foot, or 0.1 kips per foot. And what I will do is say that that's assumed. simply because it's assumed because we don't know what the shape that we're actually going to pick is. I will go ahead and give you a quick spoiler alert that the shape that we end up picking is actually lighter than 100 pounds per foot. So we don't need to go back and update that structural analysis, assuming that we have enough capacity. And you'll see what I mean when we get to that. So I'm going to take a quick drink of some water. Okay. We have a span length of 20 feet. Oh, I'll try and not do that too much in this recording, but I can't promise that I won't jerk the calculations a little bit here and there. And then we have a live load of 65 kips. Okay. And so with these, what I can do is I can say, all right, first off, our dead load moment is WL squared over 8, which is 0.1 times 20 foot squared all over 8. And when we chug that out, it ends up being 5 foot kips. Again, not a lot of moment from the self weight, because I mean we're putting a 65,000 pound load right at midspan from the live load, so we're going to get a lot more moment from that. And as we know by now, that's PL over 4, so that's 65 kips times 20 feet over 4, which ends up being 325 foot kips. And just so everybody's aware, as I'm assessing this, okay, so I'm getting all this from table 323. Okay, this is case 1, and this is case 7. Okay, I think by now, by the time this video goes live, we will have used this table quite a bit. So I did kind of go a little fast through that. But in case you're still a little rusty, you can go off of that table, or you can just do the structural analysis like we did last semester, whichever works for you. So therefore, MU is 1.2 dead plus 1.6 live. And when you chug that out, I'll go ahead and do that now. You end up getting 526 foot kips. Okay. Now for the shear, I'll go ahead and report or do the shear now. Again, as we have stated multiple times, I think at this point the shear doesn't really matter all that much for typical design. Instead, so much so I'm just going to lump all that in one formula. So 1.6 VL. So this is 1.2, and this is W naught L over 2 plus 1.6, and this is P over 2. So 1.2 times 0.1 kips per foot times 20 feet over 2 plus 1.6 times 65 kips. But I could do better with that. Over 2. And when we chug that out, we get 53.2 kips. So if you want, what I will do is I will say MU is 526 foot kips, and VU is 53.2 kips. Okay, so that part should be pretty straightforward. Again, I think we've done a few of these at this point, so I think we can move kind of fast on that. Now, one thing I am going to do is I snipped some tables out of the manual. Let me drag those down a little bit. I'll reference those here in a bit. I don't want to get too far ahead of myself, so we'll get to that here in a second. Okay, next, just like before, again, I don't think this is really anything all that different. We're going to compute IX required. Okay, so again, there's a number of ways you can do this. So what I'll do is I'll say the live load deflection limit is L over 360 in this problem. So 20 foot over 360. And then we are going to convert to inches there. And so this is 0.667 inches. And then our maximum deflection. So our maximum deflection for this problem, this is a simply supported beam with a point load at midspan. And so that expression is PL cubed over 48 EIX. Okay. And so what I'm going to do is I'm going to say, okay, delta, here I'll do this in another color just to sort of put my algebra over here. So delta limit, I'm going to set that equal to PL cubed over 48 EIX. And so all I'm going to do is I'm going to multiply both sides by IX and then divide both sides by delta limit. So therefore, I'll say that my IX required is just PL cubed over 48 E and then just delta delta limit. Pretty easy. And so the only thing you got to make sure that you do is we have 65 kips. We have 20 feet to the third. Don't forget your conversion factor. Don't forget that. And then we have 48. And then this is 0.667 inches. Okay. And so you can chug that out on your own. What you should get is, here, I'll dispense with that. You should get IX required is 968.3 inches to the fourth. And for the purposes of selecting a member, for the purposes of selecting a member for trial analysis, that's enough. We don't need any more specificity than that. Okay. So now what we're going to do is we're going to select a trial shape. Okay. And so what I'm going to do is sort of say that this is sort of like steps 3 and 4 all combined. And you'll see what I mean, because I'm going to, what I'm going to do is select the shapes and then sort of assess the deflection all at the same time. So we'll say that, so LB is 10 feet. And then we need an MU over CB. Now, one of the things I didn't state at the beginning of the problem, maybe I'll go ahead and make that point right here. There are 2 segments for this beam, and so the question might be, which one do you pick? But they are both symmetric with respect to loading, boundary conditions. They also both have the same CB, so it doesn't really matter. We're just treating them both the same. Now, CB in this case was, I told you I might do that. I'm going to try and avoid that. So MU is 526 foot kips. CB is 1.67. And so that's 314.97 foot kips. And so those are the 2 values that I'm going into the table with, is a 10 foot on the x-axis and 314.97 on the y. Okay, so now you can see sort of like why I have these tables here in the calculations, because I kind of wanted them somewhat side by side so that it would be a little easier to reference. So again, we're going 10 foot on the x, basically 315 on the y. Okay, so let's see if I can scratch that in. We'll do that in red. So basically where we're at is we're sort of like right there, and right there. just drew a big arrow there just to make sure that you all saw on the video where I pointed to. So 10 foot on the X, basically 315 on the Y. And then what I'm going to do is I'm going to go up and to the right, and I'm going to pick the first shape that I see that is a solid line, okay? And so I'm going to go up, and that's the first shape that I see right there. And if you look, what you can see is that is a W21 by 48, okay? So what I'm going to do is I'm going to write, you go away. I'm going to write a little table here, right here, is I'm going to say, okay, I'm going to give myself a little room. So trial shape, okay, and we're going to say a W21 by 48, okay. Now the MU for this problem is 526, okay. It's not the MU over CB, it's the MU. That's what we actually are designing for. The beam has to withstand a bending moment of 526 foot kips, okay. And now what I'm going to do is I'm going to write phi and P in foot kips, okay. Now, if you recall, there were two more tables I was going to include. That's IX required and IX. Okay. Those were the tables that I include if the beam has adequate or potentially has adequate flexural capacity, but if it doesn't, I'm not going to worry about filling those in. So let's see. So a W21 by 48, what I would then do, so you can see I picked that from table 310. Then what I'm going to do is I'm going to go to table 3.2 and I'm going to ask myself, for a W21 by 48, what is the phi and P? And in this case, the phi and P is 398 foot kips. Okay, so 398. And if the factored load or factored moment that's being applied to the section is 526 foot kips, and it can only have a maximum capacity of 398, this is no good. That section isn't going to work. So the way that I'm going to address that is I'm going to go to table 310 again. So I'm going to go onto the left chart and I'm going to draw upwards to the right again. And I'm going to find the next shape that works. So I draw up and to the right there. And that's the next shape. And I look at that and I see that is a W18 by 55. So now what we'll do is we'll try a W18 by 55. Okay. This is 526. Again, that's always going to be 526. What is the flexural capacity of a W18 by 55? It is, or the maximum flexural capacity. So let me be clear when I say that. That is the maximum possible flexural capacity. It's 420. Again, no good. So one thing I'll mention at this point is that I'm sure if you're following along, you feel yourself flipping back and forth. And I'm sure some of you are probably thinking, couldn't we just go to table 3.2 and find a section that works there? Can't we sort of like stop flipping back and forth? You can. There are two concerns with that. One, it's not technically the most optimal way of whittling down your section. So for example, if you look at the curve versus table 3.2, we totally skipped the W21 by 50 because in this region of the LTB plots, it's not an optimal section. It's not there. You can see the next solid lines, the W18 by 55. So that would be one point. The other point I would mention is, again, as I mentioned, or I should mention in a previous lecture, again, this is sort of a time travel thing because I'm recording this before I talk about it in class. The solid lined segments in table 310 are not always necessarily the bold rows in table 3.2. Most of the time they are, but not necessarily. So can you go off of table 3.2 to pick a section? I mean, I guess you can, but there's a chance you won't find the most optimal selection. And You know, if all it takes is a little bit of page flipping, it's not too big of a deal. Okay, so now what we're going to do is we're just going to keep chugging along. So the W18 by 55 didn't work. So what we'll do is we'll just, oh, sorry about that. So we'll just go up to the next one. And the next one I see is a W21 by 55. Maybe one thing you can do to save yourself a little bit of page turning is, if you want, you can say, let's just stick on this table for a little bit, and let's just, I don't know, maybe we can pick all of our potential sections from this plot right now. Okay, so let's see. We have, let's see, a W14 by 61. That's a possibility. Although I think I can probably find something a little better. Let's see. Or I already picked, sorry, I see that right now. I'm sorry. So I picked the W 21 by 55. How about the W18 by 60? Ooh. We can go ahead and list the W14 by 61. And then there's also, so we can do that. Yeah, that's a little better. And then we can go to right here, which is the W21 by 62. And then maybe that's enough for right now. Maybe hopefully we'll find one that works in table 3-2. So again, all these are going to have a moment of 526. 526, 526. So let's see if we can go to table 3-2, and let's start looking some of these up. Okay, so the W21 by 55, let's see what we find. So that's the W21 by 55. Its flexural moment is, or plastic moment is 473. So that section's not going to work. What about the W18 by 60? W18 by 60. Ooh, see, that is not a bolded section. See, it's got 461, so that's not going to work. Ooh, it would help if I wrote that in a pen and not a highlighter. So again, it's possible that the economic selection on table 310 does not match the bold rows on table table 3-2. 14 by 61. Here's a 14 by 61. 383. That's not going to work. What about the W21 by 62? Sorry, let me make that a little lower. I think my tables are getting a little, or my lines are kind of bunching up. So what about the 21 by 62? Okay, so let's see. The W21 by 62s, there's up top. Ooh, huh. So let's check at that. So here's the W21 by 62. It has a phi MP of 540. Interesting. So 540, this is our first shape that we found that has a phi MP that is larger than the applied moment. So what I'll do now is I'll say that one might be a candidate. That one might be worth analyzing. But there's no point in picking that section if it doesn't have the required moment of inertia. Now, if you remember, we computed 968 inches to the fourth as a required moment of inertia. And if we go to the 21 by 62, it has a moment of inertia of 1330. Okay, so this is 1330. So that should be okay. So I think what we ought to do now is we ought to try the W21 by 62, that is a feasible option for this problem. So what I will do is I will say, okay, step 5, analyze the W21 by 62 trial selection or trial shape. Now remember that I should put here a note. A note on this problem is that the W21 by 62 is lighter than assumed weight. So what that means is if we go ahead and just compute the capacity and we find it's good, we don't need to go back and update our moments like we have in maybe some of our previous problems. If it works for 100 pounds per foot, it's going to work for 62 pounds per foot. You can update that if you would like, but I'm actually going to skip that because I think we're going to be fine. So let's see what happens though. Okay, so in order to analyze the 21 by 62, because it's a discretely braced beam, what we're going to need to do is look up LP and LR to see what zone that we're in. Now for a 21 by 62, and again, you can find all this up here in this table. I think I'm just going to give you the values at this point because I don't want to scroll too much on the recording because I think that might get a little dizzying. So this is 6.25 feet, and this is 18.1 feet. And for this problem, we have an unbraced length of 10 feet. That's kind of low. Let's do it like that. So that we have an unbraced length of 10 feet. So what that means is that we're in zone 2. So in order to assess zone 2, what we're going to need is we're going to need the, let me get back to this marker. So we're going to need the CB value, which in this case is 1.67. We're going to need the PMP, which is 540 foot kips. And then we're going to need also the PBF. Remember, that's the slope of the zone 2 line, and that is 17.5 kips. And then with these, what we will do is the first thing we'll do is we'll compute that upper expression minus PBF LB minus LP. I'll tell you that practically, and I hope I mentioned this this week in class, but in case it's not there, whenever you're designing beams for lateral torsional buckling, more often than not, you end up picking beams that are zone 2 beams. That is probably the most common selection that you make. So just thought I'd throw that out there, that zone 2 just ends to be an economical pick. All right, so this is 1.67 times, let's see, 540 foot kips minus 17.5 kips times 10 feet minus 6.25 feet. And so when you chug that out, you get a value of 792.2 foot kips. So therefore, our flexural capacity is the minimum of CB times all that. I'm not going to rewrite it, or PMP, which is the minimum of 792.2 foot kips, or 540, which in this case is 540. And that's another thing with high CB problems. If you have a high CB, so I still think you should evaluate the capacity, but I would not be surprised if your capacity just ends up being the plastic moment. It's not always the case, but that more often than not will happen. So VMN is 540 foot kips, and then MU in this case was 526. So we're okay. If you would like, I went ahead and calculated the efficiency or the performance ratio, and I got 97.4%. I guess technically that's not 100% accurate, since that's going off of 100 pounds per foot assumed self-weight, and our beam's actually a little lighter, but close enough. And I will say that, I mean, dropping that weight a little bit will change the efficiency, but we're still got a very efficient design. I mean, 97% or even 96, I mean, that's really good. Now, our shear, our applied shear, we computed that as 53.2 kips. If you look up the FEVN for this beam in table 3.2, you get 252 kips. And again, that's okay. I mean, we've been saying for a while that shear wasn't really going to be an issue with most routine design. We are still going to discuss how to compute it, but we'll do that later. Let me write that as a percent. So we're going to discuss how to compute that later. We'll actually discuss that on Monday, because for bridge elements and for some elements in building design, such as transfer girders and things like that, shear can be a really big deal, and understanding at least generally how it works is something I want to impart on you all before the semester ends. Really doing hardcore shear design is an advanced steel design topic. It's not anything that anybody in the class couldn't pick up, but it's certainly something we don't really have time to cover given the limited time we have left in the rest of the semester. Okay, last thing I'll do is I will compute the deflection, just to make sure we got the right answer. So 0.667 inches. That was our limit. That's the L/360. And then the maximum deflection is PL cubed over 48 EI. Now that I actually have an EI, I can compute this out. So 65 kips times 20 feet to the third, and then throw in my unit conversion. I'm not sure why I started, a long time ago, I started doing my unit conversion factors in a different color. I think just as a reminder that you need to do them, so I thought it would highlight them. And then 1330 inches to the fourth. When you chug this out, you get 0.485 inches. And so this is good, obviously. And this is a performance ratio of 72.8%. Okay. So, do we have a selection that has both or has adequate moment and shear capacity and meets deflection requirements? Yes. Is our highest performance ratio over 90%? Yes. Although in design for stability, such as columns and beams, performance ratio it's not the be-all end-all. Again, when you go to table 3.2 or 3.10, there's only a discrete number of economical shapes. So as long as you pick the lightest one, you're good. But an efficiency ratio in this case of 90% is not a bad thing, definitely. So therefore, I think I can say that the actual answer for this problem is use a W21 by 62. So. And so hopefully this was pretty straightforward. Again, I think that there was some page flipping that you had to do, or that you're going to have to do for this. And it just sort of is what it is. There's no real way of getting around that. But like I said, is what it is. So what we're going to do is I've got a homework assignment that I'm going to give you that's somewhat similar in terms of having to do that back and forth iteration until you find a trial shape. Again, different analysis considerations and whatnot, but the same idea. And then what we're going to do next week, which is our last week of the semester, is really two things. We're going to have our final exam review on Friday, but Monday and Wednesday we're going to be tying up some loose ends. And so on Monday we're going to discuss shear design, or designing for shear, computing shear capacity. And so even when shear is so all I'll say about that is even when shear is a consideration, more often than not, you are not changing, even in bridge engineering, at least a lot of the projects that I've worked on, you're actually sizing the beam for moment and deflection, and shear is something that you come in and, I would say, quote unquote, fix later with reinforcement, such as shear stiffeners and things like that. It is a good thing to have in your head as you're initially sizing a plate girder, but even with girders where shear is a concern, it's something that you usually address after the moment and shear or moment and deflection considerations have been taken care of. But I do think it's a good idea to understand that. And then on Wednesday, what we're going to discuss is something that we've glossed over throughout the entire discussion of columns and beams, but it's something that I think we kind of need to address. And I kind of like discussing it near the end, which is local buckling. And I'll just sort of save that for our discussion on Wednesday. But with that, that's all I have, everybody. And I will see you all after the Virginia's conference on